Section 1.6 is a very short section for us. Talks about continuity. What continuity is, when I trace a graph left to right, and if I traced it, I wouldn't pick my marker off the tablet. That's called continuous. Now, mathematically, it has a lot of applications. For us, we just need a couple of things out of it. In mathematics, the term continuous has much the same meaning as it has in everyday use. To use a function, to say a function is continuous at x equals c, you're going to say that the graph is not interpreted, the graph is unbroken, and there are no holes, jumps, or gaps. All polynomials are continuous, all rationals are continuous. Let's go the other way around. What's not continuous? Domain restricted. Functions. We know of only 3. What are those? We know of rational. What about rational? If you have a over b, you want b not to equal 0. The denominator can be 0. Radicals, right? Square root, the nth root of a, if n is even. We want to make sure that this a is bigger than or equal to 0. And logs we're not going to touch on. But let's get it out of the way. We want this value to be bigger than 0. Other than that, a function is continuous, unless you're looking at a graph. Now, we have few exceptions, but we're not going to get into those as much. So let's get started. A very short section for us, for what we need. Determine whether the function is continuous on the entire number line. This has no radical, no rational, and no log. So this is, yes, continuous on the entire number line. How about this? I see a fraction. The denominator cannot equal 0. Isn't that the domain? So, any x value that you like, you can never have x equaling 3 or negative 3. That's the discontinuity. This function is not continuous at x equal negative 3 or 3. I'm going to jump to 8 next, then come back and do 6. 8, I see a fraction. I factor the denominator out. So, if I take x minus 5 into x minus 1 equaling 0, doesn't that mean x equal 5 and 1? So, I will say this is continuous everywhere except at x equal 5 or 1. Or I could just write it this way. I could say not continuous at these points. You know, if you like, you could write not continuous at x equal 5 or 1. So you're saying it's continuous everywhere except there. Here, yes, continuous everywhere. And here, instead of writing this, you could have said not continuous at x equal negative 3 or 3. No biggie. How about here? I have a fraction. Where does the denominator equal 0? The denominator can never be 0. So what do you say? This is continuous everywhere. Even though there is a fraction, but if the denominator can be 0, then there's no restriction. This is a continuous graph. If I look at number 14 and the graph is given, if I look at the graph, do you see there's a hole? Do you see if I trace the graph left to right? By the time I reach this point, I have to lift my marker off the board right there and jump. So that is not continuous at x equal 3. And we could tell right there. Now when we get to radicals, take the quantity underneath the radical, set it to be bigger than 0. Basically, you're finding the domain. X is bigger than or equal to 1, to 0, to 1, that's right. So we say f is continuous for x being bigger than or equal to 1. Right there, the domain. Here we could say f is continuous, or f is not continuous at x equal 3, whether you look at the graph or you look at that. And there's the homework, and that's pretty much all for this section. Again, mathematically, there's a lot to deal with this. For our class, we just need the domain and pay attention on the domain.